All right. So we saw in the previous hour that movement of particles on a small scale involves a number of things. So obviously, if objects are big, gravity is really important. If gravity is important, then you displace it in a medium, especially liquid medium, and obviously your buoyant force becomes substantial because you effectively replace a volume with an object. So you get a force in the in a different direction potentially. So depending on the density difference, obviously, and then you have a drag force, which is opposite to the way how you move. And then so the drag force was well, had two regimes. In a way, when objects move really fast, like cannonballs, for example, of things falling from the sky, Rayleigh and Newton had a look at that, and they saw that the force was basically scaling with the velocity to the power 2. And then Stokes did different kind of tests by putting like little spheres into a liquid, for example, silica glass bead into glycerin, and he found out that the drag force scaled linearly with velocity. The only difference being that the drag coefficient, CD, which we saw, was a function of the Reynolds number being a dimensionless number, which takes the ratio of inertial forces over viscous forces. And as a result of that, both theories came to the same conclusion. So if for a sphere, if you would take the drag coefficient to be 24 over the Reynolds number, you would get the same answer as Stokes would get. Now, if we would apply that theory to a gold sol, then we still would find that all particles would just sink to the bottom. So it wouldn't really explain why a gold sol at the Royal Society could survive for more than 150 years, because it will take, for a small particle to fall down, a couple of years in order to reach the bottom of the vial. So there was an other force in there, and then we talked about Brownian motion, the history of Brownian motion. A number of people observed this, and then finally, in 1905, Einstein wrote a groundbreaking paper on Brownian motion. Two other people contributed to that. Well, not to that paper. They wrote their own theory. So you had Marion von Smoluchowski and Paul Langevin. And the essence of the paper is on this slide. So Einstein realized that suspended particles, analogous to molecules, also had an osmotic pressure, and he applied the Van der Hoff law for osmotic pressure up to the particles, assumed Stokes' law for particle drag movement, and considered Brownian motion to be a diffusional process. So like things slowly spreading out, right? And that resulted in a definition of a diffusion coefficient, which was defined as the gas constant times the temperature over the number of Avogadro, which in a way is the same as the Boltzmann constant times the temperature, multiplied by 1 over 6 times pi times the viscosity of the medium in which the object is dispersed, times the radius of the sphere. So this equation is valid for a sphere. Yeah. Obviously, if you have a different object, it changes. Yeah. Also, this diffusion coefficient is translational motion. So it has got nothing to do with things rotating. So rotational Brownian motion is also important, but we're not going to really hardcore discuss that here because that's a little bit more tough. So let's just look at translational motion. So, and what he found that in one dimension, yeah, so only if you would look at under a microscope and you see things going in an XY plane, you see them move, and you only monitor how much they move in the X plane. You could see that the root mean square displacement of these kind of things over time. So if I would say, I'm going to look at a bead dispersed, and a second later I'm going to look again and see how much that has moved in the X direction. I'm going to multiply that with 2, because if it moves to the left, then obviously it's minus, and if it moves to the right, it's plus. So in order to get rid of that, I take the quadratic form, and then I take the root of that. So basically, I'm only ending up with positive numbers. And that should then be the same as the square root of 2 times this diffusion coefficient, which you get from the equation above, times the time. So that was developed by Einstein. And it was quite a tough derivative, well, a tough theory to understand. So Langevin's approach is way simpler. So we'll go through Langevin's approach a little bit later. He basically did it in 1A4, so it's 2 slides. And hopefully people see where it comes from. So Einstein was 1905, Smoluchowski and Langevin slightly later, so Langevin 1908. And Langevin actually discussed the mistake Smoluchowski made and corrected it and said, you made a little mistake, it shouldn't be this, therefore, but his theory was fine, he only made a small calculation error. Okay, so then we go further in time. So this other guy, so Einstein, obviously won the Nobel Prize. This guy also won a Nobel Prize. Jean-Baptiste Perrin won the Nobel Prize. And he won the Nobel Prize for some brilliant work, amongst which that he looked, at molecular kinetic theory. So trying to have the link between like kinetics, macroscopic thermo, and molecular movement. And what he did was basically he verified Einstein's theory. So he got his hands on monodispersed particles, and he got his hands on seeds from this fruit on the right. And obviously seeds from a fruit are not exactly the same size. So his students took ages, as in months, in order to sieve these through sieves to have relatively monodispersed particle size distributions of seeds of different size. So this gum-bone resin particles, well, they were sieved, and then he put them under the microscope, and then he wanted to have a look what would happen. Obviously these things would move. They would move to the left and the right and up and down, and so he wanted to verify, Einstein's theory amongst other things. So I wanted to go a little bit on why this is so great, because until that time the number of Avogadro was a rough number, yeah. And this now, if you would use the experiments that were described by Jean-Baptiste Perrin in I think his book is called Atoms. The French version is from 1910, the English version from 1916. I put a link for it a bit later. You can all the old books. You can, by the way, you can download for free and read for free on any device. So it's pretty cool. And this one is well, the translation is written in English. It's pretty accessible to read, really. So what's this based on? So he basically wanted to experimentally verify the number of Avogadro bang on by just looking at particles suspended in a liquid. And how did he do that? Well, first of all, he realized that for gases, there is a Boltzmann distribution. So how could you think that? Now, for example, the pressure of gas here on Earth, on basically sea level, obviously is higher than when you go up. So, and atoms obviously have a certain mass. So if you go further and further up in the sky, then obviously the density of these molecules potentially becomes less and less. And because if it's an ideal gas, then obviously the pressure becomes less and less. So, so what did Boltzmann figure out? Well, Boltzmann basically said that the number density of molecules of an isothermal gas, so let's assume constant temperature, in state 1 divided over state 2 is the exponential form of the potential energy of state 2 minus the potential energy over state 1 divided by kT with a minus sign in front of it. So that's, in a nutshell, the Boltzmann theory and the Boltzmann distribution. Now, potential energy for any object equals m, the mass of the molecule or the particle, times gravitational acceleration, which is g, times the height. Yeah? So if I would have my base condition saying, my base condition is height 0, yeah, so that's 0, and the other one is h, then I can basically link the state of these molecules to, well, the number distribution of the molecules to the pressure. Because if you assume ideal gas law, PV equals nRT, then pressure scales linearly with the number of molecules. Yeah? So I can interchange them, basically. because I divide them upon each other, so the correction factor doesn't really matter. So I can write an expression for the pressure at height h equals the pressure at height 0 times the exponent minus mgh divided by kT. So, and this thing is valid, so it's very fun. So you can basically say, okay, let's calculate oxygen levels on a mountaintop, and it scales pretty well. So if you know the mass of an oxygen molecule, you know how high the mountain is, you know the oxygen levels here, so you can calculate the oxygen levels, estimate the oxygen levels there. And that is called the barometric height. Now, how do you translate this to particles? Because obviously for molecules, you don't really have to correct for buoyancy in that particular case, but for particles you do. So the clever thing what Baptiste Perrin did was that he took the equation for potential energy, mgh, and corrected it for the buoyant forces. So obviously if you put a particle in a liquid medium, you get a buoyant force. So he corrects for that by basically subtracting the density of the particle, getting the density of the particle minus the density of the fluid, divided by the density of the particle. That's the correction factor. And then effectively what you get is that you get the equation from the previous slide, which had kT in it. And remember that the universal gas constant divided by the number of Avogadro is the same as the Boltzmann constant time. It's the same as the Boltzmann constant. So if you rearrange this equation, you basically get an expression for the number of Avogadro. And the number of Avogadro in this particular case is minus the gas constant times the temperature times the density of the particle, which you could measure, even for example in just like, Stokes' experiment, divided by the mass of the particle times the density of the particle minus the density of the fluid times gravitational acceleration times the height. And then the natural logarithm of the number distribution, or the number of particles at height h, divided by the number of particles at the reference state, which is called h0. And literally what he did was take a cylinder, put these particles in there, and with a microscope, he just took pictures. And he just counted the number of particles at height 1, height 2, height 3, height 4, height 5, etc. And he put it into that equation. And he got the number of Avogadro bang on, basically. So that's really cool. So this experiment is the barometric height experiment now can be done just in an undergrad lab if you want to, right? And you can calculate, verify the correct value of the number of Avogadro. Now, then there was this other experiment that Einstein described. Einstein said that, the root mean square displacement in the x direction would scale with the root of 2 times the diffusion coefficient times the temperature. And if you would fill in for the diffusion coefficient the equation that Einstein found, so kT over 6 times pi times the viscosity of the medium times the radius of the sphere, and you would rearrange this, then you would get a similar expression for the number of Avogadro. So what did they do? They literally looked down a microscope and wrote down in their lab book how these particles would move. So every data point here, you wait a certain time interval, in this case 30 seconds, and then you put on your map where the particle is then. And you do it again and again and again and again. And then, so these pictures are real pictures. They're taken from his book called Atoms. If you want to read it, there's the hyperlink at the bottom. So the interesting thing is, if you only look at the displacement in the x direction, so forget about the displacement in the y direction, and if you would fill it in this equation, again, bang on, you get the number of Avogadro. So this is, in a way, a little bit strange, because you have diffusional motion of an object on relatively long time scales, right? I'm talking 30 seconds, and then the question now is that's the diffusional velocity of the particle. But what's its intrinsic velocity? You know, what if you go all the way back to Newton's theory? What happened to half mv squared? You know, what happened to that? Half mv squared in the x direction would be the same as half kt if you link those two theories together. Where does that bit gel with this? Yeah? So Einstein predicted that the mean velocity would be the root mean square displacement, and then, you know, you divide that by time. And that effectively, if you would put that in, the top half of the equation would be root 2 times d times t. You divide that by t, so what you're left with is 2 times the diffusion coefficient divided by time, and then you take the square root of the lot. And that would basically be the mean velocity, the diffusional velocity of this particle. And this is only valid for long time scales. So there's another velocity that, you know, half mv squared equals half kt would end up with. The half kt is basically the component of the thermal energy, yeah, for translational motion in one dimension, so in the x direction. Yeah? If you want to do it in 3D, you obviously have to link that to 3 over 2 kt. Every degree of freedom is a half kt, essentially. So this story here is valid for longer timescales. And on shorter timescales, there was still a little bit of a problem. Because where does half mv squared equals half kt fit in? That's not the same answer for velocity. Whereas, you know, if you would link a macroscopic theory to internal energy, then that's what you should get. So, and that short time scale, the intrinsic velocity, is called the ballistic regime. So it's like firing a bullet, for example, right? You give it a kick, and you want to know how fast it travels before it dies out. And only until, well, 1.5 years ago, people were able to measure this in a rather bizarre extreme system for the first time. So it's very recent that this was experimentally verified, that on a shorter time scale, there's a different ruling than in the diffusional time scale. So on a short ballistic regime time scale, half mv squared, so kinetic energy, equals half kt. Now here velocity is only velocity in the x direction, right? So that's why it's half kt. So velocity in the x direction, then if you would rearrange that equation, would be square root kt over m. Yeah? So what did these guys do? They basically took a 3-micron sized silica particle and they trapped it in air with an optical trap. So with an optical tweezer, a laser beam, you can basically grab a particle. So they trap it in air and they measure its displacement. And what they found, that on very, very short time scales, with a very fast detector, they found out that Einstein's theory that, you know, basically the root mean square displacement equals 2 times d times the time, if you square that, wouldn't fit. So that's the red, the stripy line, and the black stripy line at 2 different pressures. But your time scale now is very short, so you're looking at 10 minus 6, 10 minus 5 seconds, right? Microseconds. So this plot is a double logarithmic plot. So if I would plot this linearly, so the picture on the right, you basically can see that for short time scales, few microseconds, it scales perfectly with Newton's theory for kinetic energy, half mv squared, and the link then directly to thermal energy, which is half kT. So on very short timescales, you have a ballistic regime. So a ballistic regime, what we mean is basically you have an object and you give it a kick. How long can it travel before it stops? That's the question. On a longer timescale, obviously, in a diffusional regime, it gets kicks all the time, right? Gets a kick, another kick, and it kind of spreads out over time. So diffusional longer timescale correlation, you model with Einstein, and ballistic velocities, you model with this type of equation. Now, Einstein's theory was rather complex and didn't really, well, link these two things together in an easy way. So let's have a look at, in a bit, at Langevins derivation, but first have a look at this ballistic thing. What do I mean with that, right? So with ballistic distance, I mean the distance a particle that can travel before it has no velocity left. So if I would shoot the particle into a liquid, how long does it travel before it stops moving? Yeah? So this is really important if you now go to nanotechnology. If you want to have a nanorobot, you have a little engine on it, you start your engine, you kick the gas pedal, then you get a certain energy, and you want to know when you stop moving, if you give it one kick only. Yeah, or if you shoot it into the bloodstream or something, yeah, from a device, initial velocity, you want to know how far does this thing travel before it stops. So in order to do that, you have to link two things together. So you have to make a force balance, and force is basically mass times acceleration, yeah, which is the bit on the top. So mass times acceleration, which is the first derivative of the velocity, equals, in this case, the opposing force. So if I shoot in that direction, the opposing force would be drag. And if it's a sphere, we're going to assume Stokes' law. So, and the drag force was equivalent to 6 times pi times the viscosity of the liquid times the radius of the sphere times the velocity. Yeah? And if you look at this, that's an equation that you could solve. Yeah? The v goes to the left, and you can integrate this, and the result basically is displayed on the right. So you get an expression for the velocity. The velocity at a certain time equals your starting velocity, v0, times the exponent of minus 6 times pi times the viscosity times the radius over the mass times the time. Yeah? So in a way, it's like an exponential decay. Which is logical, right? You shoot, you have an initial velocity, and you slow down because of the drag force until you don't move anymore. Yeah? So now the question is, how far can I move if I shoot something? Yeah? And because velocity is the units of that, it's meters per second, so if I would integrate velocity, then I get displacement. And I have to integrate velocity of time 0 to time infinity. Right? So let's do that. So that's the equation below. So the ballistic distance is v0, it's a constant, it's my intrinsic velocity, and then I integrate from time 0 to time infinity, take the expression from the top, and if I would do that, then basically you can see it's like an exponential decay. So for time infinity, you'll get 0, and minus times 0, an exponential one, would basically, end up in 1. So what you'll end up with, if you do this nicely, is the mass times the initial velocity divided by 6 times pi times the viscosity of the liquid times the radius. Yeah? And mass times velocity, remembering that mass times velocity links basically to kT, you can rearrange this a little bit and you get the expression on the right. Yeah? So root kT times m divided by 6 times pi times viscosity times the radius. So that's the expression for the ballistic distance. So if you know Boltzmann constants, you know, temperature, you know, the mass of the object, you can figure out. And then the viscosity of the liquid you need to know, and you need to know the radius of the object. So let's try this out in blood, right? So blood plasma in this case. Forget about the red blood cells, right? They're like rubber bands that bump around in a... So imagine, you know, you want to run into a building when everybody runs out of the building. That would be like similar, right? If you take into account all these red blood cells that bump around. Because the volume fraction of red blood cells is what? Between 50 and 60% for humans. I've heard that camels can have a higher density of red blood cells. But in that particular case, so you take a silica sphere of 3 micrometer in this case. Density of silica, 2.65 grams per cubic centimeters, can travel in blood at 37 degrees with a viscosity of 3 millipascals times seconds. So the question now is, how far can this object travel? So what is the distance this object can travel if I rely purely on thermal energy in order to basically give this thing a kick? Yeah? So what's the distance? Okay, think about this for a little bit. Try to work it out.